So good morning, guys. By the time your friends join in, good morning. Do you have any of you have any questions regarding the material we have covered so far? Till the time your friends join, do any of you have any queries regarding the material we have covered so far?
Yes, sir. Good morning. This is Ria.
Yes.
Sir, in the last class, we did make a time series object for plotting the graph, right?
Correct.
So just a doubt that, usually like in MATLAB, etc., we can basically define the x-axis as well as the y-axis. So in this case as well, since we did have a column for the date, we could have defined the x-axis, in that way. So why do we have to necessarily make a time series object?
We don't ideally, but the issue is in R, the way though there was a date column, it was characterized or it was identified in R as a character. Okay.
Okay.
It was not identified as a date variable. Okay. That is the reason, though a parameter for our understanding it was still date, it wasn't considered to be a date variable for R. So we were not able to use it. If you were to plot it using or in the plot function in R, you can specify an x-axis as well as an y-axis. Okay, the x parameter and y parameter you can do, and then do some sort of a scatter plot. Possibly that's what you are referring to, right?
Right. Yeah.
Or even if you can also mention that though it's an xy plot, you just join them using a line. That's possible. But the issue is, in that case, the x-axis, which is actually it, would have been identified in R as a character, and it would show every instance of that. So it would look a little clumsy.
Okay. Yeah. Understood.
When we are putting it as setting it up as a time series object, we are defining what is this variable going to be. Okay, and it's useful for other case also. It is not just that it helps us in plotting. It has other uses also. We are not going into those uses right now. But just to show you that even the good thing about setting up as a time series is that it's still a one-dimensional array only.
Right.
Okay, it does not become a matrix per se, but you are defining its characteristics as a time series object. Okay.
Yeah.
We'll see later on if there is a character variable in our data frame, if we can define it as a date and use it during plotting. Okay,
Right.
we're not going to there right now. We'll try to do that somewhere later in the course.
Right. So understood. Thank you.
Okay. Anyone else? Any other queries? Okay, so just a clarification. Yeah.
Just one doubt that all the files have to be saved in OneDrive, only the data files also, like in D only everything should be saved.
Can you come again, please?
All the files of that you have shared, the data files have to be saved with the R where the R files are there.
So you're saying it should all of them be in the same working directory?
Yeah. Yes.
It's not necessary. It's not necessary, but what happens is that, say for example, what if you see my R code is not in my working directory. I have kept my data folders in a single place. Okay. What happens if you set up a working directory and keep your source files is that in that case, when you are asking R to read a particular file, you don't have to specify the entire path. Okay, you can just specify the file name and R should be able to trace it. Okay, if you want to place it anywhere else, it's possible, but in that case, while you are reading that file, you need to specify the entire path rather than just the file name. Okay, it is not necessary that you keep your R code, R source file, R script, whatever you are doing in the same folder. It's possible that you keep it otherwise also. But what happens is when you set up a working directory and you're trying to save your workspace, you're trying to save your R code, that would be shown as the default directory. And when you are asking R to read any file or source any file and you don't specify the file path, you just specify the file name, by default it is going to look for it in the working directory. Okay? I hope it clarifies your doubt.
Yeah. Thank you.
Anyone else? Any other doubts? Okay, good. So just one clarification. I hope all of you understand by now and you are used to these online classes. Zoom doesn't give you the benefit of setting up classes from in 15-minute interval. Okay, so in your Moodle page, it is always going to show as 11:30, but our class is going to start at 11:45. We cannot set up Zoom in such a way that will show as 11:45. So it is always going to show as 11:30, but don't worry, the class is going to start at 11:45 and it's going to end at 2 o'clock. Okay, fine. So look, let's resume our discussion. So we are talking about assets and returns, right? So this is possibly where we ended up last time. So the question we are trying to answer is that we have heard about normal distribution, okay? And why normal distribution is important? Nothing in particular, but what happens is that if you can identify something as a normal distributed, there are certain nice properties to normal distribution that you can directly apply from there on. Okay. So last time we were trying to do this. All of you know about the bell curve. So we are talking about the bell curve. Let's start, or let's start where we ended last time. So this is our typical bell curve, right? So if these are discrete observations, so this is tentatively going to be my mean, and from my data, I can figure out what is the mean, what is the sigma. Sigma stands for standard deviation. Mu stands for mean. Okay. So if it follows one of our standard distribution, let's say if it follows my normal distribution, by the property of normal distribution, I know what is going to be the area under the boundary range of mu plus sigma to mu minus sigma, let's say. Okay, if it follows a standard normal distribution, or normal distribution per se. Okay, within plus 2 sigma to plus minus 2 sigma, plus 3 sigma to minus 3 sigma, all these are, there are boundary values. Okay, so if it falls with, if this can be classified as a normal distribution, we can say from that there are certain characteristics that we can directly say about the data. Okay, but our asset returns normally distribute. They may not be, right? So what can be the two type of deviations per se? One is, let me take another line. Okay, so this is your typical normal distribution, right? You can have another series which follows very similar pattern, but it is distributed something of this way. Okay, it's possible the curve looks similar but not same. This is definitely not normal distribution. Why? The first observations you can make is that this is not symmetrical anymore. Okay, the observations, these are not symmetrical. So what we say is that there are more number of observations. So the range within this side, so in this case, this becomes by mu, say mu 2. Okay, these values are, so to say, clustered within a short span, whereas there are multiple observations on this side. Okay, there is possibility that it's, so in this, if this is a sort of curve that you are seeing, we say in statistical terms that this is a distribution which is not normal. This is a skewed distribution. Okay, this is called positively skewed, whatever you are seeing. It's also possible that your distribution that you see is negatively skewed, right? So those of you who come from stat background can figure out that I'm not drawing the curves in a great way, but pardon me. I'm using this graphical tablets for, I would have ideally like to use the board, but I hope this makes some sort of a sense. It is the other way around, as in distribution, you are saying this is negatively skewed, and this one I'm drawing right now is positively skewed, right? Yeah. Sorry, my mistake. So here you have, so this is my positive skew. Okay, so in this case, I have a much larger range in the mu plus sigma side. Okay, so mu plus sigma, whatever you are finding, it's possible that for all of these distributions, the value of mu, the value of sigma can also be similar. Okay, just the curve will look a little different, but it's possible. Okay, but these distributions are not normal anymore. Okay, these distributions are skewed. It's also possible that we have something else. Okay, in that case, what happens is, this is a typical, the red line is our normal distribution. You can have, you can have distributions which are like this. or like this, right? So how do we identify if our series? So this is called skewed distribution. The other case where it is not symmetrical anymore, it is skewed to one of these two sides. The other case where the tail, we have a fat tail or not, that's a different property that is identified by kurtosis. So we now will try to see what all mathematical parameters can be used to identify if the series is normally distributed or not. So we talked about mean and standard deviation in our last class. There are two more parameters. One is called skewness. Okay, so skewness is called the third central moment. So first central moment was mean, second central moment was variance, third central moment is known as skewness. Okay, so it measures the symmetry of x with respect to mean, as I just showed. Okay, the way it is, the figure skewness is computed is very similar, is very intuitive also. So it's expectation of x minus mu x cubed. Okay, it's not squared. So for normal, for mean, it's just to the power 1. Okay, correct. We are normalizing to calculate this parameter. Okay, this is the normalized parameter that we are showing. You are correct, but we want to calculate this value only. For our case, we are not interested in just looking at x minus mu x cube. We want to normalize it and then use it. Okay, because that is what we can test in R. We cannot test for the entire. So what we are doing is that this Sx is being computed as expectation of x minus mu x whole cube divided by sigma xs cube. Okay. So what is the typical value for a normal distribution? It is going to be 0. The fourth central moment is known as kurtosis. Okay. So it measures the tail behavior. Is it a fat tail or is it a thin tail? Whatever. Okay. This is called, again, very similar notation. X minus mu x now becomes to the power 4 and divided by sigma x to the power 4. So kurtosis of a normal distribution is not 0. Kurtosis of a normal distribution is 3. So often, though we calculate the kx parameter, we typically want to say the excess kurtosis. So kx minus 3 is known as excess kurtosis. We check if when we want to see that if a series is normally distributed or not. What we check is we check that if the excess kurtosis is 0 or not, or if kx is 3 or not. Okay. Now lot of definitions. Let's look at some data. Okay. So what happens is that let's try to see. Okay. Before we get here, yeah. So you remember the SIBM series that we had set up, right? Simple IBM returns. We want to calculate the basic summary statistics of this data. So that we can get from the basic stats function. Okay, so basic stats of SIBM. This will compute the summary statistics. So what all information do we get here? First, we get the number of observations, NOBS. Then we get NAs as in missing observations. So our data set has 996 observations. There are no missing values. The minimum value that we see in this series is minus 0.26. Maximum we find is 0.47. You know about quartiles. So what are quartiles? So quartiles are, as if from that particular distribution, can anyone say what quartiles are? I suppose you are taught about quartiles in your first year classes. So what are quartiles? Is quartile exactly as percentile? It's 25th and 75th percentile, right? Yeah. So you know about percentile. You have come, all of you have come through CAD, so you have a fairly good understanding of percentile, right? So your 50th percentile, what is your 50th percentile? Is that mean? It's median, right? So median means there are 50% of your observations less than that value. So that becomes your median. Your first quartile is the 25th percentile. Okay, so there are 25% of observations less than. Your Q2 becomes your median, Q3 becomes third quartile. Okay, so your first quartile is minus 0.027, third quartile is 0.0517, mean becomes minus 0.013. You also get the median, you get the sum total of the entire observation, you get the standard error of the mean. Can anyone tell me what is standard error? What is standard error? And why is it useful? What is standard error? Can you come again, please? The voice was not very clear.
Standard.
Hello.
Is this?
Hello.
Yes.
Standard error is how true the data is to the population, basically. So
Is that standard error?
uh, how much does it deviate from the true? So the deviation, basically, it says.
Is it just a measure of deviation? That's what you're saying. Then you have standard deviation, right? What is standard deviation and what is standard error?
So standard error is normalized by the size of the sample. So standard error is basically standard deviation upon under root of n. So
okay. And why is it useful?
So for comparison purposes, if we have two samples whose size is different, then standard error might be a good measure to compare them.
How? So you're saying, for example, I have, so all of you get the concept of population and sample, right? So population is about what we are trying to make some conjecture, but in practice, we don't have access to the population. What we have access to is a sample of that data. Okay, so using the sample data, we are trying to make some sort of a conjecture about the population, right? Now tell me, if you get two samples from your entire population, how does standard error help you? So you have, what you're trying to say is, let me just try to put it into some sort of figures, what you're saying, and then try to see. So you're saying this is useful when you're talking about sample. So let's talk about sample 1 and let's talk about sample 2. I'm spending some time here because I think these are concepts which should be clear to all of you, because this is going to be applicable everywhere, not just time series analysis. Okay, so you have, what you get here is, let's say you have n1 number of observations. The mean you figured out is sigma 1, and standard deviation you calculated is sigma 2. Here you have a sample which is n2. This is mu2. This is sigma 2, and you have a population. Both of these sample is drawn from the population, but the population in itself is unobserved. You don't have access to the population data. You have access to sample 1 and you have access to sample 2. Okay. Now how does what is standard error for, say, sample 1, and how does that help you? Yes, Ria, you want to say something?
Yeah, so for sample 1, the standard error will be sigma 1 by under root of n1.
So this is going to be sigma 1 by square root of n1. And similarly
sigma
for
2,
here,
yes.
Yeah, this is going to be the standard error. Yeah, and how is this useful?
So standard error is basically the deviation of this sample mean, which is basically sigma 1 from the population mean.
Okay, from the population mean.
Yeah.
So the way this is actually useful is, most of you got it correct, but if I want to make it, let me try to say that this is, what is the usefulness of this one? I want to test something. I want to say that, is this value, I know this is mu, okay, or I want to test if this is mu. Saurabh, you wanted to add something?
No, sir.
Okay, okay. So if I do something like this, so this is, let's say, mu, okay. I want to test about the sample. So this is my mu. I want to test if the population mean is mu. Okay. I have access to the sample. Okay. Now, what happens here? Sample mean, let's say, is mu1. Okay. Now, based on the difference of these two, I want to say that some sort of a boundary range, and I want to test if it is possible for me to statistically test if the sample mean is statistically equal to mu, or is it not. Okay, so we'll see shortly how that's going to be useful. Okay, so standard error, your definition is correct. It is the standard deviation, sample standard deviation divided by square root of number of observation for that particular sample. Okay. Okay. So you have variance, you have standard deviation, you have also skewness and kurtosis. Okay. See, skewness, ideally it should have been 0. So it is not 0, it is 0.43. Kurtosis, it should have been 3, but it is not 3, it is 3.43. Now the question is, based on this, can you see this is normal or not? Possibly not. These need to be statistically significant or not. Okay, we need to test if these values are statistically significant or not. For that, what we can do is that we can run individual t-test. Okay, so you have heard about t-test, I hope, right? You have heard about t-distribution, you have heard about t-test. So we can run individual t-test to check if Sx, the value we got, if that is equal to 0 or not, okay, or if the excess kurtosis is equal to 0 or not. These are individual tests. A better way to test for that would be the Jacques-Berer test. Can it help to find difference in performance of an ETF from a benchmark? So think about it. Is that sample you are saying, is that a part of your observation? Because this is useful when you are trying to make conjecture about sample from population. So think about it, try to see how you can put it as sample from population. Okay, think about it, Jay. So what? Yeah. So what Jacques-Berer did is that they tried to come up with a consolidated or a single test statistics that will tell you if this is statistically significant or not, or if this particular distribution is normal or not. Okay. So we are talking about being normal or not based on whether skewness is 0 and whether excess kurtosis is 0 or if kurtosis is 3. So what Jacques-Berer did is, Jacques-Berer test statistics is SR square divided by 6 by T, 6 upon T, where T is the number of observations that you have, plus KR minus 3 whole square divided by 24 by T. This statistics is asymptotically distributed as a chi-square random variable with 2 degrees of freedom. This we use to test the normality of RT. Now let's try to apply this to our data. Okay. So this is how you calculate descriptive statistics from the total data. Okay. So if you don't want all of these parameters, if you are looking for only certain parameters, that is also possible. You can calculate, refer to them individually. So you can test for mean, variance, square root of variance. It doesn't have a direct parameter for standard deviation. You calculate the variance, and from variance you take square root and figure out standard deviation. You also can calculate skewness, kurtosis. These would give you the exact same values. I'm just trying to demonstrate that without getting the whole list of entire test statistics, if you're looking or if you're interested in individual test statistics, that also you can do through this method. Now here what we are trying to do is that we are trying to see the t-test. We want to check if the mean return for this particular series is it 0 or not. Okay, that we do through t-test. So this is one sample t-test. Okay, so again, as I just mentioned, essentially what's happening is that we are trying to see something like this. We have an observed value where we have an observed line, so to say, and from that data we calculated some sort of a mu hat. This is based on my data. Okay, and you also have some sort of say sigma plus sigma minus sigma. Okay, this basically means mu naught plus sigma, or let me put at or prime for all of them. So this is mu prime is my observed data. I also calculate the standard deviation. What I want to test for that is if this value is statistically different from 0 or not. So what is the intuition behind it? If let's say this line is here and this is my 0 line. Okay, this is my 0 line. That means based on this distribution, if this follows a t-distribution, this 0 line is far off from mu prime. In that case, possibly we can say this is, I'm trying to put it in layman terms. This is not me trying to put it in statistical terms, just to give an intuition how this thing works, right? So if mu naught is far away from the 0 line, okay, based on the same value of sigma, then possibly we can say this is statistically different from 0. Instead, if this is not the case, if we have another situation whereby the 0 line is over here, okay, possibly in this case, this mu prime is not that far away from the 0 line. How do you say far away? This we calculate through the standard error. Okay, if this difference divided by the standard error, that is within a specified range, where if it follows a t-distribution, it is going to be within the range of plus 1.96 to minus 1.96. If it falls within that range, possibly this is not statistically different from 0. Okay, do we always test for 0? It may not be. We can test for some arbitrary predetermined value as well. We can also test whether these returns are statistically different from 10%. Okay, so here what we are trying to do is that we want to see through a t-test if the mean return for this SIBM series is it different from 0 or not. So what you see, the t value is 5.93, degrees of freedom being n minus 1, so 996 observation. The p value is very low, so 3.958 e to the power minus 09. So this is almost 0. Your alternative hypothesis is that true value is not equal to 0. Okay, this is also gives you the 95% confidence intervals. So basically trying to say that based on your observation, based on your number of observations, so sigma and n, and if you want to test if it is equal to 0, if it falls within the range of 0.009 to 0.178, possibly you cannot say that it is statistically different. So the result shows that the hypothesis of 0 expected return can be rejected at 1% level. Why 1%? Because the p-value is very low. Okay, you can also say it is true at 0.1% statistical significance level or even higher. Okay, but here 0 expected return is not the case. Okay, thus definitely this value is not 0. Okay, my expected return is not 0. Clear to all of you? Any doubts at this point of time? I have set up an alternative screen whereby I can see your chat windows. So yeah, don't mind me looking other way at all times. So if there are no queries, I would assume that you got it, right? This part is clear to all of you.
So one doubt.
Yes.
Why have we kept the true mean as 0 and not anything else? Like you said that we could have kept it as 10% also.
No, so 10%, that's a different case. Here, the t-test that you are seeing, okay, what we are essentially testing for is how this t-test works. So you have, based on your data, what you're essentially doing is that, so the t-test designed in R is by default a test for if it is different from 0 or not. Okay. If you want to test it for any other values, or if it is different from any other pre-specified value, you need to use a different case statistic. But let me just tell you how the mechanics of it work. Okay. So from your data, you have a mu1. Okay. You have sigma 1, you have n1 based on your data. Whenever we are talking about data, we are basically saying the data you have is basically sample 1. Okay. You want to test if this is equal to some sort of a predefined mu, which is, let's say in our case, we tested if mu equals to 0. We set up mu equals to 0. It's also possible that we set up mu equal to 0.1. Okay. Right now we want to test for if mu equals to 0 or not. So what we are basically doing is that we are taking the difference. So mu1 minus mu divided by the standard error. So this is basically sigma 1 divided by 210. Okay. This is our test statistic. Okay. Now based on which side it is, let's say your mu1 is 0.05. Okay. Your sigma 1, let's say is 0.2. And your number of observations is root, or number of observations is, let's say 400. I'm intentionally making it higher so that it becomes easy to compute. So root n becomes 20. Okay. So what is happening here is your mu1 is 0.05. Okay. Minus your mu, let's say that is 0 at this point of time. Sigma 1 is 0.2 and this is 20. Right. So this becomes 0.05 divided by this becomes 0.01. So this is your t-stat, right? So in this case, your t-stat comes out to be 5, okay, which is outside the range of. So what is this range of plus 1.96 to minus 1.96 about the t-stat I was talking about? This is based on a 95% confidence interval based on your t distribution. Okay. So if this is outside the range of plus 1.96 to minus 1.96, it's very well possible that it is minus 1.56, right? So you can just change it to minus and you will find that this comes out to be minus 5. Okay. But it is still outside the range of plus 1.96 to minus 1.96. If that be the case, your mean return is statistically different from the value of 0. Now let's see if I make it instead of 0. Let me cross out this part. For the same data, you now have 0.15. Okay. Now what happens now? The same case statistic is now going to be 0.015 divided by 0.01, which comes out to be 1.5. Okay. Now, based on this data, this is not outside this boundary range. This falls within this boundary range. So you cannot reject the hypothesis that actually the population mean is 0. Okay. So the sample you have drawn is giving you a mean return of 1.5%, but actually based on the standard error, this is actually 0, or this is not statistically different from 0 at 95% confidence interval or 5% level. Okay, is this clear now?
Yes, sir. Actually, I was just asking why have we put mu as 0? Is it because we have made an assumption, or do we
Yeah,
have
yeah,
an
yeah.
idea about the population?
What happens is that in case of financial data, in many cases there is an assumption of zero mean return. Okay, so if you're looking for daily level observations, it is possible that there is some sort of a mean reversal that happens. Okay, we want to see if that is true. But is it actually going to be true in all cases? There may not be, right? There may be some sort of, so what happens is the stock price keeps on going up and down, right? In different periods. We are testing is, based on my data, is the mean return that we are seeing, is it statistically equal to zero or not? Okay, based on my daily level observations.
Okay. Yes, I got it. Thank you.
Yeah, yeah. If you have a different series, how would you have tested just using the same data? So you have a different series. So let's say you have a series, say YT, okay, and you want to see if this sample is for some other stock. Let's say for TCS stock. So we are talking about monthly returns, right? So we want to test if the TCS monthly returns, is it statistically different for 1% return. So from the entire series, we could have subtracted this 0.01, and done the same test. We would have given you the same result. Okay. Don't worry, as you move further, this is the first time you are seeing these things. As you move on further, I hope these things will be clearer to you. Okay, now again, let's go back to our primary question where so at this point of time, all we said is that we have seen some sort of an description of the data in terms of the basic parameters. There's a function whereby we can see it at one glance all the basic parameters, as in the mean, standard deviation, median, first quartile, third quartile, variance, skewness, kurtosis being displayed in one go. We also did a t-test whereby we could test if the mean returns were different from zero or not. So remember, this is monthly data. So 1926 to 2008, I get monthly data. What you are saying is that based on whatever we have seen so far, at least we can say the mean returns are statistically different from zero. This is definitely not zero. Okay. So now we want to, as you remember, right? So here we talk that we can run individual t-test to check if the skewness and kurtosis is zero. Okay, this is us running those individual t-tests. So you remember skewness, SIBM gave you the skewness value, which I think was skewness value was 0.44, right? 0.4388, and kurtosis was 3.44. So what you can do here is that this I am storing in a variable S1. Okay, so skewness SIBM would give you 0.44. That I'm storing in a variable S1. Okay, and now I'm computing the t-test statistic. Okay, because you remember this one. So if you are testing for equal to 0, so mu minus mu bar divided by standard error, that is our t-test statistics. T-stat. Okay. Now, if mu bar you are testing if it is equal to 0 or not, it effectively becomes mu by standard error. Okay. It can be shown that for skewness, okay, if it follows a t distribution, that value comes out to be 6 by t. You remember in the same parameter we used, right? So 6 by t. So we are testing it individually. So S1 divided by 6 by t, if that is, so this is pretty high. Okay, so based on this, it seems that the skewness is statistically different from 0. Skewness is not definitely 0. And there is one more test statistic. So whenever we are talking about t-stat, okay, t-stat is a parameter which we use to make inferences, But in that case, we also need to say about the confidence intervals, right? There is another way to take for test for statistical significance, right? Which is p-value. Can anyone tell me what p-value is? We have heard about t-stat. What is p-value?
It is the minimum confidence level at which you can reject the null hypothesis.
Yes, yes. So basically that is based on whatever, so p-value is size independent, right? It just tells you at what statistical significance level it can be tested, right? So here, instead of testing for this particular value and comparing it with our benchmark figures of say 1.96 to minus 1.96, instead we are computing the p-value, okay? P-value can be computed this way. So I'm not going to the conversion. If any of you are interested, I'll send you some material about how to convert p-values to p-values. It's going to take a long time. But what we are looking for from the p-value is that this p-value should be small enough. Okay. P-value can be directly compared with the statistical significance level. Okay. So if you want to say something with say 5 at 5% statistical significance level or 95% confidence interval level, you are looking for this value to be less than 0.05. Definitely the p-value that you see is less than 0.05. Okay. Here, this is the Jacques-Bera method. Jacques-Bera method is this one. So first we tested if skewness was statistically different from 0 using a t-test. Just to show you, we don't use that much in practice. We definitely use the Jacques-Bera test in more in practice. Okay. So here we are for our test. We're testing if the SIBM series is normally distributed using the Jacques-Bera method. So this is normal test SIBM method JB. So this is the Jacques-Bera normality test. This is the statistics as you find. P-value is less than 2.2 e to the power minus 16. So this is absolutely small. So the result shows the normality of sample returns is rejected. That means based on the data we have, it cannot be said that these values are or this distribution of returns of IBM are normally distributed. These are not normally distributed. Yes, Jay, you want to say something? Jay, you wanted to say something?
Yes, sir. So in P confidence interval,
Yeah.
so it is 95%. So it is confidence interval is basically two tail, na? So 2.5% on each side, right? So it should be less than 2.5% p value or less than 5% only.
No, p value gives you an aggregate figure. P value gives you an aggregate figure, right?
Okay.
So here we are comparing p value, which should be less than. So what we are saying is a one-sided test versus a two-sided test, right? We just want to know this is a two-sided test. Okay. We want to know if this value is different from 0 or not. It can be on either side. Okay. We are not testing if this is less than 0 or greater than 0. This is on both sides. So what you are saying is basically the area under the curve should be, is it 95% or higher or not, right?
Yeah.
So basically from this statistics, this p-value is absolutely small. 2.2 e to the power minus 60 is absolutely small. We are going to compare it with the 5% level, which is 0.05, and make a conjecture that the normality is our initial hypothesis that is rejected. Our null hypothesis was this data, SIBM is normally distributed. We are rejecting that null hypothesis. We cannot say that this data is normally distributed. Okay.
Okay, so it does not matter whether it is 2 or 1 tail. So p-value.
Here we are not testing for one-sided. We are by default testing for two-sided. Okay. The p-value result that you are going to get, just test it with your confidence interval level. Okay.
Okay. Thank you.
Yeah. Yeah. So what about log returns? We initially started with simple returns, right? We also talked that there is something called log returns. Are the log returns normally listed for SIBM? As you can see from this particular table, it's not true. Okay, even for the log returns, the Jagpera test statistics is very small. The p-value is very small. It basically says that the normality for log returns even is rejected. Okay, so neither the simple returns nor the series based on log returns are normally distributed. This series is not normally distributed. Okay. Now let's move further. There is something called stationarity. Okay, this is an important consideration while talking about time series analysis in particular. So what do we mean by stationarity? So what was the initial premise of time series analysis? That adjacent observations are dependent, right? So if you're talking about YT, then YT seems to be dependent on YT minus 1, okay? Or even further. To make such conjectures, we need to check if this particular series is stationary or not. Let us try to define stationarity now. So a time series, there is something called strictly stationary, okay? So it is said to be strictly stationary if the joint distribution of RT1, if you move further till RTK, is identical to shifting. That means this might seem little too much of jargons for some of you. So let's see something like this. You have some sort of an observation of some data. Okay, this is a series YT. Okay. Now I am working with this data. Yeah, you got another sample, which was this data. So this is sample 1 and this is sample 2. Okay, mind it, both of these are for the same security. Okay, we want to know if this is stationary or not. How do you make that conjecture? Effectively, what you're saying is that if the distribution of these observations is identical to the distribution of these observations, then possibly we can make a conjecture that this particular series is stationary. So stationary in time, it does not matter where you start your observations from. This set of observations seem to be distributed in an identical way. Are series always stationary? No. But if those can be set stationary, then we can make some useful arguments about that. Okay. So this RT1, T1 is some sort of a time parameter till Tk. We just want to show if we shift this entire series by an amount of T. So all these suffixes, we are adding a parameter T. Even then, if we find that this joint distribution is identical, then we can say that this is strictly stationary. Okay, don't get worried by the mathematics because you are not physically going to test for all of this. Your statistical package is going to test for it, but you need to understand the notion of what is that this package is testing, what is that this statistical tool is testing. Okay, so if this is true, if the joint distribution of this series is identical, then we can say it is stationary. But in practice, strictly stationary, we don't observe in many cases. What we observe in many cases, or what we test for in many cases, is called weakly stationary. Okay, so what does weakly stationary mean? A time series is called weakly stationary if both the mean of RT and the covariance between RT and T minus L are time invariant, where L is an arbitrary integer. That means, let's go back here. Let's go back to our whiteboard. So if we see that this is my mean mu1, this is mu2. If these means are same, if these are not function of where you are beginning from, okay, this was T1 till Tk, this one T1 plus T till T1 Tk plus T, okay. So if it doesn't matter where you start your observations from, you still observe the same mean, and the covariance between these two is independent of the shift, then possibly we can say that the series is weakly stationary. Okay, any doubts? Any doubts so far? Do we need two samples with equal size? See here, essentially the sample size in both these cases are tk, right? So there are k number of observations in both cases. So yes, essentially when you're talking about this particular test, so physically do understand that we don't, select these observations and test it. Okay, we are going to do that, but here what we are essentially trying to say is that forget about k. You have k number of observations, that can be 100, that can be 1000, but you take 1000 observations starting from one time and 1000 observations starting from a different point in time. If you still find that the means are same and the covariance between RT and T minus L, okay, so T is one series. If you say what is going to be T and T minus L, rather, yeah, let me do some. Okay. Fine. Just give me a time. Give me some time. I'll set it up in Excel, some of your data point, and then possibly show it to you. I think that would be easier for you to understand. Yeah. So this is the data set we saw, right? All of you can see this Excel file, right? So this is the date parameter and IBM results. Okay. So this is essentially your RT that you are testing. If we now say that let's shift this, okay, what do I mean by shift this? So let me write this as RT, and this becomes your R of T minus 6. Okay. This is one series. This is another series. This is RT as you observed it. This is RT minus 6. So basically your observation here has been shifted 8 times, right? If the covariance between these two, okay, if the covariance between these two, so what, this is RT and RT minus L. If these are time invariant, where L is an arbitrary integer, then we can say it is weakly stationary. In mathematical term, what do you mean? RT is weakly stationary if E of RT equals to mu, which is a constant. So at any point of time you see, you take these observations, the mean is always constant. And second, the covariant of RT and RT minus L. So RT is your observed series, RT minus L is L shifted series. Okay, the same series shifted by L terms. That's a function of L only. That's not a function of T anymore. In that case, we can say this particular series is weakly stationary. Okay, all of you with me till this point? Yeah. Thank you. So what happens when you have weakly stationary? In applications, weakly stationary enables us to make inferences concerning future. So we can make predictions. Okay. So if a series is not weakly stationary, so let's talk about what sort of a series would you say is a weakly stationary series and what is not. Let's talk about, you know about COVID data, right? All of you are keeping tabs. Is the number of people getting affected, the total number of people affected, just think about that data. Does it seem it's a stationary data? I'm not talking about any sort of statistical test. I'm just talking about apply your mind. Is it going to be a stationary data? Right? It is not, right? Because if you take some sort of first thing was to test if the mean was seen. Okay. So as in, if you take some sort of a rolling average, okay, let's say 7-day rolling average, or 10-day rolling average, or 30-day rolling average. This has been increasing over time, right? Mean number of people getting affected, that is changing over time. So it is definitely not a stationary series. What about the daily number of people getting infected? Is that a stationary series? Unfortunately, even that's not, right? Unfortunately, even that's not affected, or the daily number of people infected in India. This also has an increasing pattern. So even that's not a data set possibly which can be considered stationary. Okay, so net people affected, net people infected, is that a stationary series? Or rather, let me put it there, net people affected. So net people affected as in number of new infected minus the number of people recovered minus the number of people who have died. Okay, is that can that be a stationary series? So let's see some data regarding that. Okay, so all of you must have seen this. Sorry. Right. I hope all of you can see my web browser. You must have seen this data, so I'm not talking about the source of this data. Forget about cumulative. Let's look at daily. India. So confirmed number of cases. Definitely, this is not active cases. Is this stationary? Even this we find that there is a possibility that it can be, but we are not sure. Okay, it seems that there is there a pattern to it? Not recognizable, but at least it is not exponentially increasing like the other series, right? So there's a faint possibility that this particular net chain series can be considered stationary, but that definitely the others are not stationary. Okay, so if we go for any one state, let's say Delhi. Okay, what happens in Delhi? So Delhi, this is confirmed. Okay, this is active. So here it is possible that this series is actually stationary. Okay, may not be because there was a negative turn night. Now there is, but if you take the last few days, there is some sort of an indication that it can be stationary also, right? So now you have a fairly good idea what a stationary series can be and what a non-stationary series can be. Okay, or at least there are some series outright which you can classify as this cannot be a stationary series, right? Okay, so what happens with stock price? Is it possible the stock price is a stationary series? Yeah, is it possible stock price is a stationary series? Over a long time cannot be. Okay, because there seems to be some sort of a growth in stock prices, right? Over a long period of time, every stock based on the riskiness, there is some sort of a trend. So yes, prices, if you look at stock prices, typically those won't be stationary series, but returns can definitely be stationary. Okay, because returns can be stationary time series, it might be possible for us to model them through time series models and make future predictions. Are you getting what I'm trying to say? If something is non-stationary, then it can blow out of your idea. Okay, it can grow to a range where it becomes not impossible to predict. Okay, but if a series is considered stationary, it may be possible to model them through time series or through traditional time series models and then make prediction. Okay, so we can make only time series prediction models for series which are at least weakly stationary. Okay. So in finance literature, we commonly assume that asset return series is weakly stationary. Remember very carefully, asset returns, not asset prices. Okay. The assumption can be checked empirically for provided you have a significant number of historical observations available with you. Okay. Any questions so far? Is stationarity dependent on whether moving average is similar across observations? So rather, let me put it this way. If a series is stationary, then you should find that the moving average over time remains constant. Okay, does that help, Taki? Yeah, but it is so it's the other way around. So what I'm saying is that if it is stationary, then the moving average should be constant. But does it ensure that if the moving average is constant, the series will be weakly stationary? No, it does not. It does not ensure that. It is not the single criterion based on which stationarity should be computed. Stationarity, as we showed, needs to, if it is weakly stationary, these two conditions need to be satisfied. E of RT needs to be constant, and covariance of between RT and RT minus L needs to be a function of the difference only. It cannot be a function of time. It cannot be a function of when your observations start from. Okay. Okay. So I think we are supposed to have a break. So it's a good point possibly. Before we move to correlation and autocorrelation, let's take a break. Come back. It's 12:45. Let's come back and resume by 1 o'clock. Okay. So let's get started. Yeah. In the meantime, let me respond to a few of your questions that I got in the meantime. So, high growth financial asset will have a constant moving average, but it may not be stationary. That's possible. Okay, that's possible that that is the return series which has a constant moving average. Why does it need to have be a high growth? Even a low growth financial asset can also have, right? Even in that case, it's possible that it has some sort of a constant growth. Whether the growth parameter in itself, the mean value is high or low, that's a different question altogether. Okay, but if it is constant over time, then it passes one of the tests, but it may not pass the second test, which is the covariance needs to be a function of the difference only. It cannot be a difference of when you are testing. Okay, so yeah, from that perspective, so the covariance between a series starting from 1960s and the covariance of series. So let's consider that you are testing with 3 years of data, right? 3 years of monthly data. Now, whether so if it is weekly stationary, then that covariance parameter that you are checking. Let's take that one series is the usual series that you're seeing. The another series which is RT minus L that you take as 3-month difference series, right? So basically the return series and the 3-month lag return series. So the covariance between these two series, if it is computed based on the 1960s or 1990s or now, if that is just a function of what difference you are, so 3 months, then it should be stationary. If not, then it's not non-stationary. Another question I got is that okay, I see a lot of questions in one window and not too many in the other. Okay, let me try to address some of the other questions. Okay, so how does stationarity help in prediction? So we are essentially trying to say that these models that we are going to talk about shortly, starting with ARIMA models, these are linear time series models. What you are saying is that in order for us to use these models to make inferences about or make predictions about future returns, we need them to be weakly stationary. Okay, so what I'm going to do is that we are going to start off with an assumption of them. We'll start off with return series. We'll assume that the return series is weakly stationary and then start building up our model. Then we'll relax that assumption. We'll test it, whether the series is stationary or not, and what sort of adjustments do you need to make in our data to make sure that it fits the model. Okay, so right now we are going to inherently assume that whatever return series we are discussing or whatever return series we are considering, these are weakly stationary. We are not going to explicitly test for their stationarity. Later on, relatively later on in the class, we would relax that inherent assumption, test for it statistically, and make corrections in the model if it is not so. I hope that possibly answers your queries. Is there any other query regarding the material covered so far? Okay. Then you move to something called correlation and autocorrelation, right? Correlation, I suppose, is a concept that you already have a fair bit of knowledge about. Autocorrelation may not be that much. but we are going to talk about what autocorrelation means in our case. Okay. So what is correlation? Let's consider two random variables, right? So two random variables x and y. The correlation between these two, or the correlation coefficient between these two series, is basically some sort of an indication how closely these two series are related. Okay, and how closely these two series move uh, with each other. If the movement in one series is mimicked closely by another series, we typically say that these two series are correlated. If it is not so, then we see these two series are uncorrelated. Okay. Say for example, typically you would find that if you just have a measure of height and weight of people, you would find that there is some sort of a correlation, right? But say height and IQ may not be, right? There may not be any direct relation. Weight and IQ may not be, right? But height and weight, yes, there can be some sort of a causal relation between these two, and it is possible that the series would be correlated also. So typically, the way we compute correlation is, covariance, right? So correlation coefficient between these two variables x and y can be defined as covariance of x and y divided by the square root of the product of variance, or you can say standard deviation of x multiplied by standard deviation of y. So square root of variance of x is standard deviation of x, and square root of variance of y becomes standard deviation of y. So covariance divided by the product of standard deviations, or covariance divided by the square root of product of covariances. Okay. So if we want to put it in terms of expectation, this is how equation 9 is what it looks like. Expectation of x minus mu x multiplied by y minus mu y. So you have an x series, you have an y series. Let me try to show you that using simple series in Excel. I hope all of you know this, but still, this is a sort of a recap. Okay, so this is my observations. This is, let's say, series X. This is, let's say, series Y. So we have 15 observations, a series X and a series Y. I am freezing these two series. Okay. So I want to calculate the covariance. So for that, first I need to compute the mean. Okay. So mean of this series would be nothing but the average of series X and average of series Y. So I can compute X minus mu X and Y minus mu Y. So mu Y is basically the mean. Mu X is the mean of X. Mu Y is the mean of Y. So this would be this one subtracted. Freeze this one. I'm not defining the individual steps because I think this would be all easy for you to understand. So what happens with expectation? So covariance, I want to compute. So covariance is computed as expectation of x minus mu x multiplied by y minus mu y. Okay. So this becomes x minus mu x times y minus mu y. Expectation is basically your average, right? Because there is no other probability of this series given to you. So this would be simple average. Okay. Now covariance in itself is a scale dependent parameter. So to make it scale independent, we use covariance. So mean and standard deviation would be STDV. Sample or population, this is sample standard deviation. So we have this one, we have this one. Okay, standard deviation of X, standard deviation of Y. So the way to compute this, one way to do this is, this is the covariance, okay, and this one you can compute through just divide by the covariance divided by, so this divided by this multiplied by this one, okay. So correlation is this one. Alternatively, as it was shown to you, x minus mu x as whole square and y minus mu y whole square. Expectation you take, so basically you take the average of squared, you take the square root, you get those values, right? So this is what we basically did, the sample counterpart. So expectation is, it comes from the definition, okay. If you are given a data set, you basically do it this way, okay. You take the sum total, okay, of these observations. So basically there will be n on both sides and that will basically cancel each other out. Okay, so you can compute the correlation coefficient. So correlation coefficient, what's the beauty of correlation coefficient? By definition, it is within the range of -1 to +1, where -1 suggests perfect negative correlation, +1 suggests perfect positive correlation. Most practical purposes, you will get a value within the range of -1 to +1, where zero correlation defines that there is absolutely no association between two series. Okay, fine, all good so far. This correlation, I suppose all of you know. Now this is something that you may not be used to. So autocorrelation function. So what do you mean by autocorrelation? So let's start off with a weakly stationary return series RT. Okay, so when we're talking about, we're looking for some sort of a linear dependence between RT and RT minus L. What do you mean by that? That RT can be modeled as a linear function of RT minus L. What's a linear function? What's a linear function and what is a non-linear function? Let's talk about x and y. If I say y is a linear function of x, and if I say y is a non-linear function of x, what is the distinction that I'm making? Linear function is a polynomial with degree 1, okay, and for non-linear, if you're talking about linear function, let's not say polynomial with a degree 1, because polynomial by definition means there are higher order terms present, right? So there are no higher order terms present in a linear function. It is just x, no x square, no x cube, nothing, right? If it is just a linear function of x, that means it can be written as something like an a plus bx, but a and b are constant and you just have x term. If it is in the form of a plus bx plus cx square, it is no longer a linear function. Okay. Anything else? What's a non-linear? Is it just about polynomials? It can be a log function also, right? So y equal to 3 log x, is that a linear function or a non-linear function? Y equals to 3 log x, is that a linear function or a non-linear function? Okay, good. So when you're talking about linear dependence, right? So linear dependence between RT and RT minus well. The concept of correlation is generalized to autocorrelation. That means now we are not talking about two different series. We are talking earlier about a series X and a series Y, and we are talking about the correlation coefficient. When you're talking about now two series, but they are not X and Y. This is RT, so your time series as you have it, and RT minus L. So the same time series but displaced by a value of L. Okay. These two series that you have, the correlation between these two series is called autocorrelation. Okay. So are you seeing this presentation? Oh, sorry. Sorry, you were possibly were seeing the Excel file as of now. So this is the correlation coefficient that we have, right? We defined it through the Excel file. Now let's consider a weakly stationary series RT. When you're talking about the correlation coefficient between RT and RT minus 1, correlation is generalized as autocorrelation. So if this is RT and T minus L, so there's a displacement of L, we call it is an L order autocorrelation. Okay, it is commonly denoted by rho L, and under the weakly stationarity assumption, this is a function of L only. Okay, so let's see how that would look like. So lag L autocorrelation of a series RT is basically, as you can see from the earlier series, this is covariance between RT and RT minus L, and divided by the variance of RT and RT minus L. Now, if it is a weakly stationary series, this variance of RT and variance of RT, so variance of RT is going to be equal to variance of RT minus L. So the denominator here basically reduces to just variance of RT. So you have covariance of RT minus L divided by variance of RT. We now designating it as rho L divided by rho 0. Okay, sorry, not rho, this is gamma, right? So gamma L divided by gamma 0. By definition, gamma L would be, sorry, there's a mistake in the notation. By definition, rho L, which is the lag L autocorrelation, this I have to correct. This is not gamma L within -1 to +1, but rho L will be within the range of -1 to +1. Okay. So a weakly stationary series RT is not serially auto. So serial autocorrelation, we have possibly heard about this particular term being used in other courses. Okay, is there serial autocorrelation present in this particular series or not? Okay, it can be used in the concepts related to finance, it can be related to economics, it can be related to strategy. There are various series where we are concerned whether there is serial autocorrelation in that particular series or not. A weakly stationary series RT is serially correlated if and only if rho L equals to 0 for all L greater than 0. So if all the higher order autocorrelations are statistically equal to 0, only then we can say that the serial or there is no serial autocorrelation present in the series. So each observation in that series is independent of the historical value. Okay. So this is just the lag L autocorrelation definition, and this is the sample counterpart. So how do you use it from your data? Okay. So T to T minus 2, this is rho L. Yeah, I suppose this is understandable. Okay. So let's try to see what do you mean by that. Okay. So what I am doing is that now we have a series RT. Okay. We want to check for this order L autocorrelation. So it is possible that we change this value of L and get different values. Okay. Consider the entire series. We displace it by 1 and compute the autocorrelation. We displace it by 2 and compute the autocorrelation. So this is IBM stock returns from 1926 to 2008. Please consider we are not testing for weakly stationarity or not, that we assume, and then we start testing for this autocorrelation function. Okay. So what you would find is that what would be lag 0 autocorrelation? Lag 0 autocorrelation means the series and you're testing the correlation with the same series, right? So in that case, the correlation coefficient should be 1. That's what you find. In order 0, the correlation coefficient is 1. Okay. Now you find that there are the next values are pretty small. Okay. What are these two blue bands? These two are basically the horizontal dashed line are two standard error limits. Okay. So we want to check whether any of these are statistically significant or not. Here we are finding that beyond order 0, most of it are not statistically significant. Okay. So the serial dependence in IBM monthly stock returns for the sample we have considered is very low. At least that's what shows from this graph. Problem with the way we are seeing this graph is, so ACF is the function that we are using. Okay, ACF is IBM. If you don't specify lag max, then it is going to test, I think, till 30. I think the default is 30. Plot equals to true. In that case, it will come up with the plot, not otherwise. Okay. So if I wanted to show you what happens when I go till 100 max. Okay. So this is how it looks like. Okay. But the problem is that there is a problem of scale. You always know order 0 autocorrelation is going to be 1. That's by definition, right? So it doesn't make sense to plot it. Whether you plot it or not, it is always going to be 1. And to test whether the rest are significant or not, it's better if you skip that one, right? If you don't see that one. So what I do here in the next case is that we are going for another plot, but here we are dropping the order 0 autocorrelation, okay? To have a better understanding of how many of these higher order autocorrelations are statistically significant or not, okay? So what we are doing here, you see here, look at this function within. So let me just try to do this in Excel. In R, I think it will be easier for you. Okay, I hope now you are seeing my R screen. Yeah. Yeah. Okay. So what we are doing right now is, yeah, possibly I still have to read a few of these data files. So let me read the data and let me store it in SIBM. Possibly still need the libraries FBasics and ggplot2. Yeah. Okay. That. So now, if what I did last time was ACF of SIBM, right? If I just hit this, what happens? You get to see the plot. Okay. What is the max order? It is 40 right now. Okay, this is pre-specified by R. If you want tweaking in this, you put in lag max equals to 50. In that case, it increases the plot, the x-axis range till 50. Okay, what I did last time, lag max, if I put it 100, I go till 100. Okay. The question is, this one value at lag 0 or order 0 is always going to be 1. So I ideally want to drop that. Okay. So what I do now is I make these corrections whereby I.
Hello, sir. Can you hear me, please?
Yes. Tell me.
So you are typing in the screen. It is coming at the very end. I am not able to see. I'm not sure about others, but it is coming at the very end, so I'm not able to see your screen. The down part, wherever you're typing.
Okay. So
If you
it will
can
be
scroll it a bit up.
okay.
Thank you, sir.
Okay. So you are saying that the lower part of my shared screen is not clearly visible to you?
Yes, sir. So the last part I can see is ACF SIBM lag max is equal to 50.
Okay. The rest you are not able to see. Okay. Fine. Does it matter now, or is it the same?
Yes, sir. Yes, sir.
It's better now, right?
Thank you.
Yeah. So I don't have to actually write this because you have already have the entire code in the presentation also. So actually what I was doing is that I was not writing in a script. I was writing it directly in the console. That's why there might be this issue, but still, let me see. Okay.
It's visible right now.
So what I did here is that yeah, possibly I can go back to this one. So what I'm changing right now is I am not plotting using the traditional function. Okay. What I'm doing is that if you see, I'm putting in ACF LIBM lag max. Now plot equals to true was my last argument. I'm changing it to plot equals to F. Okay. Now what will happen is that now the return type, there would be an array which R will store. Okay. Now this will be from the start. It's as most statistical packages, it will start from parameter 0 till parameter 100. There will be 101 values starting from lag 0 till lag 100. So what I'm doing is that I am just taking 1 to 100. I'm dropping the rest. Okay. So I'm dropping the lag 0 value. Okay. And then I am plotting it. So I have an array. From that array, I'm just choosing I'm dropping the first observation and taking the rest. Next is y limit. So again, I think it would be better if I show you the coding in R. Okay, so these are done right now. Yeah, this is what you had, right? ACF. Now what I'm changing is that SIBM lag here instead of true, I'm putting in false. Okay. Now what happens if I execute it? You would find that it is basically showing me 100 values. Okay. Now I'm changing it to 1 to 100. Okay. And I'm executing that single line again. You'll find it's almost same, just the lag 0 value has been dropped. Okay. Now I am putting the plot function and I'm plotting this value. Now what will happen? It will show the curve dropping the lag 0. Okay. So it suppresses the lag 0 ACF, which is 1, and it shows till 1 to 100. Okay. Now, if I want to make it even better, what I did last time was that I specified the y limit within the range. So, y limit I specified, okay, and also a title I specified. I'm not very keen on typing those things again. You can read from the slide, okay, and write down later on. So, y limit is basically specifies within which limit it will show. So it is -0.2 to +0.2 main. Okay. Now what you see here, and you can see from the data in the our output also, that here we have now a better understanding. What you see here is that in the short run, at least 1, 2, these are not very highly statistically significant. Okay. So it is just within that boundary. The rest values are low, but we have some higher order terms which are statistically significant. Okay. But possibly it is not a very great idea to go with modeling based on those values. Okay. We are not talking about how to model based on what you observe, but just to show you that there is autocorrelation function indicates that based on my higher order terms, there is some sort of a autocorrelation. That was the SIBM series. What I have given you is for the LIBM series. You can try it out. Okay. Here we are doing it the IBM log returns. Okay. Okay, so IBM ACF log returns, it shows that most of these values are within the statistical significant range. We don't find many of these So the CDL dependence in the IBM log return data is very low. Okay, it's not very high enough. So our statistical financial applications, we often require to test jointly that several of the autocorrelations are together zero. It is not to test whether row 1 is 0, row 2 is 0, row 3 is 0. We want to test our null hypothesis, which is row 1, row 2, row m, everything is 0. So we just want to specify what is m. Okay. So for that, Box and peers, they came up with the Portmanteau statistic. Okay, which basically does is that this is something similar to all of you have done regression, right? So what happens in regression? We basically sum square the error and try to minimize that error, right? We square up the error terms and then try to minimize it by adjusting the slope parameter and coefficient parameter for whatever value for which we get those values to be the error value to be minimum. We said this is the best fitted regression based on the OLS model. Here we are trying to do something similar. So by default, row 1, row 2, row m, all of these parameters should be, if Box and peers, we want to test them as 0. So this is, we take the square of it. Okay. Now, based on certain conditions, this is asymptotically chi-squared random variable with m degrees of freedom. Because it follows a predefined statistical distribution, we can test for it using the statistical test. So Portmanteau is one of these ways we can test whether several of these autocorrelations are 0 or not. Together they are 0 or not. Okay. Now Portmanteau is the basic thing. Okay. Based on that foundation, what Box did was that they improved upon it further to increase the power of this test statistic. So there is a slight modification whereby from the earlier model they multiply it with a constant term, which is t multiplied by t plus 2. But t is the number of observation, and divide this parameter divided by t minus l. Decision rule is that h naught, what was h naught for us? That all of these together are 0. We reject h naught if qm, the test statistics, is greater than chi-square alpha, where chi-square alpha denotes the 100 multiplied by 1 minus alpha percentile of the distribution with m degrees of freedom. Okay. So what is this choice of m? So as you can see, the choice of m can affect the performance of the statistic. So what you're going to do is that, let's say you have a data series which has t number of observations, which in our last case was 996. Okay, it has been shown that if you choose an m which is close to ln t, so natural logarithm of t, then it should give us good idea. Okay. So if you take natural logarithm also, how do you calculate natural logarithm in R? If you just type in log, so log of, let's say 100, it will calculate natural logarithm of 100. Okay. The default is ln. Though you are typing log, by default R computes a natural logarithm. If you want log base 10, you need to use a different function, which is log 10. Okay. So based on our data, you can see that the value suggested for m would be 6. Okay. So it seems that if we test for 6 orders of autocorrelation, we should get a fair enough idea. Okay. Now what I want to do is that instead of using 6, I'm just showing you what happens when I change these parameters slightly. So we want to go for the Box test. So what are we testing? We want to test that all the ACFs apart from 0 are jointly 0. Is that true or is it not? Okay. So based on the Box test, we are taking a lag 5. So m in the last case, I am specifying that as 5. Box test here, SIBM lag 5 type u, you will find that the p value, because now we know that p value is scale independent, it just directly gives you the result. So p value is high enough, right? If p value is high enough, do we reject the null hypothesis or not? If p value is very high, do we reject the null hypothesis? We don't, right? So here we are not able to reject the null hypothesis that all the higher order autocorrelations are 0. Okay. So here we have to accept the null hypothesis, right? That means Based on the test statistics we see here, it seems that all the autocorrelation ACFs, apart from ACF at lag 0, are statistically equal to 0. Okay, that was evident from the graph also, right? Here, what you saw was all of them were within the 2 standard error boundary. This is just to give you a graphical idea. When you are testing them statistically, it showed the same results. What happens if I change this from lag 5 to lag 10? Okay, even now you find the p-values are high enough. So p-values in both cases are high enough. So the null hypothesis that all the ACFs are 0 cannot be rejected. So the IBM series, what do we know so far? This is a monthly IBM series we are talking so far. We have statistically tested the mean is not 0. Mean is different, statistically different from 0. There does not seem to be any serial autocorrelation present in this data. Okay, these are the interpretations we have made from this data so far. So the 2 sample ACFs, the plots, are very close to each other, whether you are considering the log returns or simple returns. And serial correlation of our monthly IBM stock returns are very small. Okay. Yeah, we didn't test for portmanteau statistics because we have an improved version, which is a Loom box test. Okay. Now what we are doing is that, is it always going to be this way, or there is some other version as well, or some other variation as well? So what we are doing right now is, instead of single stock returns, what happens if we want to take the aggregate market returns? So remember, go back to our original data. The data we imported had data on the IBM returns. We also had data on the value weighted index and equally weighted index. Now we are going to run the same test that we have for serial correlation, but instead of running it for the single stock, we are going to run it on the market as a whole. Okay. So this is the CRSP value weighted index. We just stored it in the SCRSP variable. DA was our original data frame where we got the data. We also converted it to log returns. Okay. Now I'm plotting the ACFs. Now you see that it is pretty different, right? So what do you see? Tell me. What do you make out of this particular graph? What does it see? Use your intuition. Whatever we have discussed so far, use your intuition. Tell me, what do you see here? Ravish says low serial correlation. Anyone else wants to say something? Guys, if you guys don't speak up, then it is going to be an extremely boring lecture series for me and for you. No stationarity. Abhishek, are we testing for stationarity? I told you we assumed stationarity in the first place and then started with the ACFs. Okay, we did not tell you anything about stationary test for stationarity. Devan says there is high autocorrelation in lag 1, 3. Yes, you may say that. Anything else? For lower lag values, the ACF is not 0. Technically, it basically, you can say that the ACFs are statistically different from 0, right? It fails the test. Why do you mean failing the test? It's not like I giving you a hard paper and you fail the test, right? We want to check if there is serial correlation in this data or not. Now you tell me if there is serial correlation in this data, yes or no. There is, Jay says there is autocorrelation. So my question is this data serially correlated, yes or no? What about others? What do you think? If you guys don't start speaking up, possibly I'll have to request all of you to turn on your videos and figure out whether you are alive or not. What do you mean by serial correlation? Can you explain it? Exactly. So now I understand that you have a definition, you have a difficulty in understanding the concept, in grasping the concept of serial correlation. Okay, higher number of factors. Saurabh, I'll definitely explain that, don't worry. Higher number of factors crossing the threshold line. Okay, so when do we see serial correlation? When there is high amount of correlation between the values that you see and the lagged values. Then we see there is a serial correlation with the data, or the data is autocorrelated. Okay, or when you're talking about autocorrelation of the order we need to specify. If it is first order autocorrelation, that means the observed values and one period lag. If it is order 2 autocorrelation, then whatever you see and lag 2s, lag 3s, that way you keep on changing. Okay, that's the order. Now, when we talk about serial correlation being present in the data, we want to know whether this autocorrelation of the order 1, 2, 3, whatever, if you go on further, order 0 autocorrelation is always going to be 1, that is by definition. But what about 1, 2, 3, 4, 5, 6, 7, 8, 9, 10? If these are statistically different from 0, we say that the data is serially correlated, otherwise no. Okay, now you tell me, is this data serially correlated or not? Saurabh, what do you think now? Why? You are finding that lag 1, lag 3, lag 5, lag 9, all of these are statistically, or at least from the plot, these are crossing the threshold lines. That means these are statistically significant. If these are statistically significant, that means there is serial autocorrelation in the data, right? If these were, look at the difference from the IBM plot, right? Here, all of these ACF values were within the boundary. Here, many of these values are outside the boundary. Okay, that means these are statistically significant. It does not matter the latter ones. If we find that even some of them are crossing, there is serial autocorrelation. Okay, for serial autocorrelation, it is not essential that there would be dependence. So think about it. Apply your normal intuition. Is it likely that today's returns would be correlated with last month's return or returns 50 months from now? Think about it. Are today's return going to be more dependent on last month's return or returns 50 months from now? More likely for the last month, right? So in that case, you should expect that if at least lag 1, if you find that is significant, that means there is strong dependence between last month's return and this month's return. Okay. If you find that in lag 12 there is this thing, you can say there is some sort of a seasonality. Okay. What if the latter ones are crossing and initial ones are not? Yes. If that is the case, then there is some long-term relation. In that case, the model becomes a little more difficult. If you find that the short lags or the initial lags or the lower order lags are statistically insignificant, but higher order lags are statistically significant, the model becomes more cumbersome. If you find plots like this where the near or smaller order autocorrelations are significant and higher orders are not, it becomes much more easier. We'll see how to make inferences. Here I'm not saying that this is going to be a model which just looks at 1, 3, 5, 9. No. We are going to go more test on how to model this data, but this is just to give an idea where do we find an association. So based on what we observe right now, we are finding some sort of an association between whatever return series you have and the return series 1 period lag. Also something 3 period lag, 5 period lag, 6, 7, 8, 9 period lag, and so on and so forth. Okay, so some of these autocorrelations are statistically significant, or we did not check for statistical significance. This is just from the plot. Okay, how do I make that decision based on the Ewing box test? Let's see. How do the threshold limits what do? So two standard errors, right? So you know the mean, two standard errors is basically the plot. Okay, but don't worry, we are not going to use that lines to make the comment that we are saying. For that, we'll use the Ewing box test. Okay, I just showed you the Ewing box test statistic some time back, right? So here we are going to use the Ewing box test. First, we are going to use the simple returns. Here we find that unlike last time where the p-value was pretty high, now the p-values are pretty low. Okay, so we are not able, so now we can reject the null hypothesis whereby all the ACFs were 0. Okay, so here we are not able to make that conjecture either for SCRSP, which is the simple returns, or log returns, both cases. Whether you go for lag 5, lag 10, doesn't make too much of a difference. In all cases, you are finding that the p-values are small enough. So some of these values, some of these serial or some of these ACF values are statistically different from 0. Not all of them are equal to 0. Okay, so in that case, we are saying that there is serially, this value weighted index is serially correlated. So monthly market index seem to have stronger serial dependence than the individual stock returns. Is it theoretical? To some extent, yes, but most of it is empirical, what you observe in practice. Okay. Got so far? Seems good enough? Right? Okay. There are a couple of more terminologies. Just get yourself acquainted with these two. There is something called white noise, and there is something called a linear time series. Okay. So what's a white noise? So a particular time series RT is called white noise if this is a sequence of independent and identically distributed random variable. Okay. IID, independent and identically distributed. I'm not going to give you the definition. Look it up. What does it mean? And how is it different from whatever you have understood so far? Okay. So if these are IID random variable with finite mean and variance. Okay. So what does this mean? If RT is normally distributed with mean 0 and variance sigma square. Okay. Mean 0, variance sigma square. This is called a Gaussian white series. Okay. What happens in that case? Why is this important for us? For a white noise series, all the ACFs are 0. Okay. So it seems that for the IBM returns data, all the ACFs were 0, right? Is that a white noise series in this case? It's possible. Okay. It is possible. In practice, if all the sample ACFs are close to 0, then this is called a white noise series. So based on our observation so far, we may say that the monthly IBM return series that we got, that was a white noise series. Okay, there was no serial dependence. That was a white noise series. Okay, so what next comes linear time series. So what happens now? So in this case, you have RT equals to, now there's a constant term. Okay, the return there is always some sort of a constant finite term, and then you have several AT minus. What is this AT minus 1? This is a sequence of IID random variable with mean 0 and well-defined distribution. So ATs are basically a white noise series. So what happens is that you have a white noise series. So what happens with white noise series? All the ACFs are 0. Okay. Now, if you add up several white noise series and add some constant term with it, okay, then you have something which is known as a linear model. What happens to the linear model? AT denotes, this is particularly useful in terms of modeling stock. So why? AT, there's a possibility that you can think of RT being the stock price, mu being the drift parameter, okay, average returns, and AT is the new information coming in time t, and it is often referred to as innovation or shock in time t. Okay. So return in every period, there is a fixed term which it should be based on the fundamentals, and there is some spike. That spike can be upward, that can be downward, depending on what sort of information there is. Okay. There is an important personal step down, that's negative information. You added one more factory to your existing corporation, that's a positive news. So every period, based on the fundamentals, there is a mean expected return expected, which is mu, and then you add up something or subtract something based on new information which is coming. So in that case, what happens to the expectation? So E of RT, this is a white noise series, a second parameter, right? A summation of white noise series. If there's a white noise series, summation of that is going to be 0. Okay. So expectation E of AT is always going to be 0. So E of sum of AT, that's also going to be 0. So second part does not come in the mean part. So E of RT is going to be just mean. Okay. What happens with variance? Constant term doesn't have any variance. So variance of mu is 0. What happens to the next part? That becomes sigma A square summation of I equals to 1 to infinity psi I. Psi I basically the weights. Okay. Clear so far? Yeah. Don't worry, as we go further, we will have better understanding of what this individual terminologies mean. Okay. But do you have any question regarding the material I have covered so far? Or else I'll get started with the AR models.
Sir, Devayan here.
Yes.
Sir, will it be summation of psi I square?
Possibly yes. I missed that notation. Yes. Yes. It will be summation of psi I square. Yeah. True. Thank you.
So what does phi I mean? What does it denote?
Psi I, you are saying?
Yeah.
Okay. That is basically the coefficients, right? We are trying to build up a model where these are the coefficients that are there. ATs are white noise series, okay? And this is the coefficient that you have for each of these series, okay? This is, so see, in most of our cases, we won't be having a model like this. This is just something you should know, okay? Don't be bothered about, we are not going to try to model it this way. We are going to try to model it some other way. But psi I is just the coefficient. You run a regression model, you get the coefficients beta. So these are something similar to the beta.
Okay. Thank you.
Yeah.
Hello, sir.
Yes.
So like if the ACF of the IBM returns is white noise, if we assume that, like if we get through that.
No,
So,
let me just correct the terminology. The ACFs of IBM were statistically not different from 0.
okay.
So basically, we made a conjecture that the return series is basically a white noise series.
What is the implication, like real world? What do we conclude from that? Basically, that I wanted to know.
So what is a white noise series? The white noise series is more of a random series. There is no pattern to it. It becomes difficult to predict that series. Okay. So every time some new information comes, there is going to be a change, but you cannot predict tomorrow's value based on today's value. If there is serial dependence in the data, it becomes easier for you to assign some sort of a weightage, okay, and then have a prediction of tomorrow's model based on today's model. But if it is a white noise series, what is going to be the returns tomorrow? Your guess is as good as mine.
Okay.
Okay. If it is a white noise series, then basically you don't have a fair idea about tomorrow's return. If it is not a white noise series, if there is a serial dependence in the data, then it might be possible for you to make a conjecture about tomorrow's expected returns based on today or past values. Does that answer your question, Jay?
Yeah, that it does.
Okay. Okay.
Thank you.
Any other queries?
Sir, we assumed that it is not statistically different from 0. Now,
We
what
did not assume it. We tested it.
Yeah, so we tested it. So if we test that it is not statistically different from 0.05,
It doesn't make a difference. It doesn't make a difference. We just want to know whether it is 0 or not.
Okay.
Okay, we are not really bothered about the value of that. Okay, we just want to know, is it statistically 0 or is it not? If it is 0, so what is the implication of this? basically this weight is going to be translated somehow in the model, how much of today's return you can predict using yesterday's values, something of that sort. Okay, so that weight is immaterial. I just want to know whether I can do that or not. Okay, if these all of these ACFs are statistically equal to 0, then I cannot predict tomorrow's value based on today's value. But if there is some sort of a serial dependence, possibly I can do that. How much of it weight should be given to today's value? How much of it should be given to 7-day prior value? How much of it should be given to 12-day prior value? That's a different business altogether.
Okay, sir. Thank you, sir.
Yeah. Any other queries? Okay, fine. So now let's see. Yeah. So this is the material on AR series. So what is an AR series? So AR stands for auto-regressive. Okay. So what did you observe so far? Based on the data we had, we saw that the monthly return RT of CRSP value weighted index had a statistically significant lag 1 autocorrelation. Forget about the higher orders. At least lag 1 autocorrelation was statistically different from 0. Okay. This indicates that the lagged return RT minus 1 may be a useful information in predicting RT. Okay. So what happens if we build up a model like this, where RT equals to phi 0, a constant term, plus phi 1, RT minus 1 plus AT. This is called an auto-regressive model. Why? Because each period you have an RT, you build it on your RT minus 1, then use it to predict one period future. Okay, so your RT, there is only, it is a function of RT minus 1. So what is phi 0? Phi 0 is a constant term. What is A0? What is AT? It's a white noise series with a mean 0 and variance sigma A square. Okay, so constant variance, finite variance, but mean 0. Okay, so it may go up to 0.1 in one case and minus 0.05 in the other, but the mean value of AT is going to be 0. So over a period of time, if you aggregate it, AT will cancel out. Okay. So in the time series literature, this sort of model is known as an AR1 model, or in other words, it's an auto-regressive model of order 1. Why order 1? Because you only have RT minus 1 in the model. Okay. We don't have RT minus 2 or RT minus 3. We are not saying this is just based on the ACF graph. If we are saying that if RT minus 1 seems to be a good information to predict RT, this is the one way you can build your model. This is a linear model. Why? Because there are no, the coefficients phi 0, phi 1, these are not parameters of T. Okay, so this seems very similar to your regression models. Okay, but instead of your cross-section regression models where you had Y and X parameters at the same point of time, this is the same series. You are using one value for today to predict value for tomorrow. Okay, or value of yesterday to predict value of today. Okay, so what does this model signify? Are there what sort of inferences can we draw? So expectation of RT. This is not just expectation, this is going to be conditional expectation, right? Just a second. Somehow my chat window vanished. Let me see. Yeah. If it is RT minus 3, is it still AR? Absolutely it is. Okay. If you can have higher order AR models. Here we are starting with a simplified model. Okay. where we have phi 1 RT minus 1. There may be phi 2 RT minus 2, phi 3 RT minus 3, so on and so forth. In that case, what is the order of that model? The highest lag you have. Where the highest lag you have is 1. So this is an AR1 model. As you go on further, you can have AR2, AR3 models as well. Okay. So what can we say about the expectation of RT? So if you think about expectation of RT, that is going to be a conditional expectation on the value of RT minus 1. So what happens in that case? Phi 0 remains, right? So phi 0 remains, phi 1 RT minus 1, what happens with that? So it becomes expectation of RT given RT minus 1 is going to be phi 0 plus phi 1 RT minus 1. What happens to variance? Variance would be variance of RT given RT minus 1 is going to be sigma A squared. Okay. Straightforward generalization of AR1 model is the ARP model. Okay. Remember, this is not variance of RT. That we'll see what happens. This is conditional variance of RT given RT minus 1. Okay. So straightforward generalization of AR1 model is the ARP model where you have higher order lags also. It is not true that if you have an ARP model, all the P coefficients, which are phi 1, phi 2, phi 3, phi 4, phi 5, all of them would be statistically significant? No. Many of them would be 0. You have seen your regression model, right? All of you have seen multiple regression models. All of you are used to multiple regression models, right? Yeah. So you have seen that you keep on testing, you include different parameters or different values into your model. But as you keep on changing, as you keep on testing, you will find some of these coefficients come out to be 0. Then you drop them from your model. We'll do something very similar here. Okay. If we find some of these are statistically not significant, we'll drop them from the model itself. Okay. But then what is the model of the ARP model? Which is the highest order of lag you have. Here it is still order P. So this is an ARP model. Okay. Fine. It seems a good time to stop today's session. You have any queries? Okay, so what I'm planning to do is that I've seen that some of you have filled up, most of you have filled up the group assignment, the group spreadsheet that I have shared. I'll check it and I'll let you know the final group formations. And what I'm planning to do is that I'll set up a Q&A forum in your course page. Okay, if you have some better alternative, please let me know. If you have any queries, please post it. You can write a mail to me. Okay. If I feel that's more specific to your question, I'll respond to you only. If I think that's a generalizable query, okay, with the response may help others also, then I'll basically take it and anonymously put it, or I won't specify your name. I'll put it in the forum as a question. I'll also post my response to it. Okay. I've been trying it with one of my other courses. These are all experimentations that we are doing. If any of you have any concerns regarding them, please let me know. If you have other better suggestions, I'm happy to explore. I'm trying to come up with some way whereby our learning is improved, right? The most that we can get out of this particular not so pleasant scenario. Okay, so feel free to write to me or post it in the forum. I'll try my best to respond to it. I may not be able to respond to all of those queries. If there's a time constraint, I'll try to prioritize the questions which I think are more important. But feel free to do so. And if you have some better alternatives, suggestions, please absolutely go for it. Okay. Thank you guys. I'll upload the material today. Okay. I'll upload the entire presentation for last day. I'll remove the presentation which is already uploaded because that was a part of my presentation. I'll upload my entire presentation for the time series introduction. I'll also upload the material for the introduction to AR models, which I'm just starting, and the R code, which might be needed for you to run the models yourself. Please do so. It will give you need to do that. You do it as a practice. You have the data files. I'll give you the code. Please do so. Okay. Thank you. Take care, guys. Bye.